Welcome to the third tutorial on electric power systems. We will be discussing on power system supply lines. The first problem that we are going to solve is what is the percentage saving in feeder copper if the line voltage in a two-wire DC system is raised from 200 volts to 400 volts for the same power transmitted over the same distance and having the same power loss. So the case A that we are taking, or the one we are taking, is basically a DC system, which is a two-wire DC system, and case B is also a DC system, two wire, but the voltage that we are increasing from 200 volts to 400 volts, keeping something constant, that is the power transmission, distance and power loss. So we have to determine what is the percentage saving, in copper. What is the percentage saving in copper? So that is being asked in the problem number 1. So let us see the solution. The two cases that we have for the DC system, one is having a 200 volts, another has in 400 volts, and we know that power is equal to voltage into current. So we can create two cases, 200 I1 and 400 I2, as both the powers are same for the two cases. Then on equating the powers, 200 I1 is equal to 400 I2, we can find out the relationship between I2 and I1. So we are getting I2 is equal to 0.5 times the current I1. Then after that we can find out the losses. So losses will be represented with W. So losses is equal to the current square into the resistance, and N will be the number of conductors that you have. So the two cases that we have, W1 is equal to 2 I1 square into R1, and W2 is equal to 2 I2 square into R2. We can substitute the value of I2 as 0.51 in this equation. So we will get 0.5 I1 square into R2. After that, we have to equate the power loss because it is same, W1 is equal to W2. So after equating that, we are getting 2 I1 square R1 is equal to 0.5 I1 square R2. So from this relationship, we can find out that R2 by R1 is equal to 4, and we know that R is equal to rho L by A. So the resistance and area of cross section are inversely proportional to each other. So area will be A1 by A2 is equal to 4. Also we know that the volume is proportional to the area. So V1 and area are equal. V1 is proportional to A1 and V2 is proportional to A2. So you have the volume V2 by V1 is equal to 1 by 4, which is equal to 0.25. So we have the percentage saving in the copper will be in the two cases. In the first case we have V1, and in the second case we have V2. We will take the reference as the first case into 100. So if we put the formulas of the volume of the copper, we can divide V1 and V1 in the both the terms. So what we are getting, this V1 and V1 cancel it out each other. So we are getting 1, and V2 by V1 we can put as 0.25. So we are having 75%. So it means that when we increase the voltage from 200 volts to 400 volts for the same system, we are having 75% saving in the copper. So this is completes the problem number 1. In the problem number 2, we have a DC two-wire system. So this is DC two-wire system which is converted to three-phase, three-wire AC system. So this is basically three-phase, three-wire AC system. So you can see that this is the first conductor, this is the second, and this is the third. So you have three phases, and here you have DC two-wire system. So this is the first, and this is the second conductor. Now it has been told that the third conductor is having the same cross-sectional area as the two existing conductors. So third conductors will have the same cross-sectional area as the other two conductors. Calculate the percentage additional load which can now be supplied. So when we convert the DC 2 wire into three-phase 4-wire system, so how much load we can have additional, keeping the voltage between the wires and percentage loss in the line remain unchanged. So we have to get the same voltage and the loss, percentage loss, has to be the same. So assuming that the system is balanced and load is of unity power factor condition, so cos phi is equal to 1. So in all the solutions for the problem, we will assume that R is the resistance per conductor in each phase. So R is basically the resistance, R will basically the resistance per conductor per phase. So this will be assumption for all our problems. Now we have basically two cases, two-wire DC system and three-phase, three-wire AC system. We will have a comparison formula symbolically. So power 1 subscript we are taking for the first case. So this is the first case and this is the second case. So P1 is equal to voltage into current, because we know that in DC system your power is voltage into current. However, in AC system your voltage is root 3 times the line voltage, line current cos phi. There is a power factor, or 3 times the Vp, that is the phase voltage, into the phase current into the power factor. So any formula you can use. Here we are using voltage into current. So here you have root 3 voltage into current, because we have assumed that the power factor is unity. Next, the power loss is 2 times the I square R, and here we have 3 times I square R, because here we have 3 conductors and in the DC system we have 2 conductors. So percentage power loss then we can find out as what is the loss divided by the total power into 100. So for both the cases we can find out the percentage power loss. Now we can equate that percentage power loss, we can equate, because it has been told that same loss is being taken place in both the conductors. So in that case, after solving this, we are finding a relationship between I1 and I2. So 2I1 is equal to root 3 I2, where we can find out I2 is equal to 2 by root 3 times I1. So after that, we know that the load we have to find out. So load basically means the power, how much power we are basically transmitting. So P2 by P1, if we find out the relationship and the I1 and I2 relationship that we have deduced, we can substitute here. We can find out that P2 is basically 2 times P1. It means the power is increased to 100% when we are using three-phase, three-wire AC system, provided we are keeping the power factor cos phi as unity and the load is balanced. This completes the problem number 2. Problem number 3, we are using a DC 3-wire system. So you can see that here we have 3 wires, whereas the central wire is the neutral wire, which is converted into 3-phase 4-wire system. So here you have 3-phase and the 4th wire is basically your neutral wire. So 4th wire is a neutral wire. Now you have to find out the percentage power loss and voltage at the two terminals, which are remaining to be same for the two cases. What is the extra power that is being given at unity power factor condition at supplied by the AC system? Again, the load is balanced. So similarly to the previous problems, we will try to solve these problems on the similar ground. So here again the resistance will be assumed to be the conductor per phase and load is balanced. So neutral wire will not carry any current. If the neutral wire is not carrying any current, so there will be no power loss. Now we will have a comparison of 3-wire DC system with 3-phase 4-wire AC system. So power basically in DC system we know that it is voltage into current, but since it is told to be you have 3-wire where the second wire you don't neutral wire you don't have any current flowing, so it is 2 times the voltage into current, and loss again will be 2I1 square R. So this is the percentage power loss which we try to find out using loss divided by total power. In 3-phase 4-wire system, the 4th wire is the neutral wire, so we do not take into consideration because the 4th wire is not carrying any current. So power is equal to 3 times the voltage into current. Assuming the power factor to be unity, loss will be 3 times I2 square R. So the percentage power loss is, we can find out at the loss by power into 100. Now, if we equate the two conditions, if we equate, we are trying to find out I1 is equal to I2. If you have I1 equal to I2 and the power condition P2 by P1 if we use and substitute I1 equal to I2, we are getting P2 is equal to 1.5 times P1, which means there is an increase of 50% in the 4th wire. So when we have a 3-phase 4-wire system, your extra power is 50% increase compared to your earlier system. Now problem number 4, you have a comparison of single phase AC system. So this is single phase AC system. The load that is given is 200 kilowatt. So here you can transmit a load of 200 kilowatt, transmit a power that supplies a load of 200 kilowatt, and you have a 3-phase. So this is 3-phase 3-wire AC system which is running in the 3rd similar conductor. So if you have a 3-phase load that can now be supplied with a voltage between the conductor to be the same, assuming the power factor and transmission efficiency to be the same in the 2 cases. So you have to see how much power load we can give when the system is converted from a single phase system to a 3-phase 3-wire system. So again we can assume R to be the resistance per conductor per phase, and power factor in both the conditions has to be told to be keeping the same. So just compare single phase 2-wire AC system with 3-phase 3-wire AC system. We know that in AC system the formula is voltage, current and cos phi. So here you can use voltage, current and cos phi as single phase system, but here you have to use root 3 times because it is a line quantity. So you have line voltage, line current and cos phi, and loss here you will have 2 conductors, so 2I1 square R. Here you have 3 conductors, so loss will be 3 times I2 square R. Then you can find out the percentage power loss with loss divided by power into 100. In both the cases you have to do, and then you can equate the losses for both the cases. You equate it for both the cases, so you will find a relationship between the current and both the currents. So I2 is equal to 2 by root 3 times I1. Now you have to see how much power the second case is giving with respect to the first case. So P2 by P1 you find out, substituting the current to be I2 equal to 2 by root 3 I1. So you are getting that P2 is equal to 2 times the power P1. It is told that the P1 is 200 kilowatt. So power 2 is basically 400 kilowatt. So there is 100% additional load you can give if you convert the system to 3-phase 3-wire system. Now the next problem, problem number 5. Here you have a 50 kilometer long transmission line which is supplying a load of 5 MVA, 0.8 power factor lagging and 33 kV. So the things to be noted here is that the unit is MVA. So this is basically the complex power given. This is 0.8 power factor, so basically the power factor information is given, and the 33 kV voltage is given. So this is basically the line voltage and not the phase voltage. The efficiency of the transmission line is given to be 90%. Calculate the volume of aluminum conductor required for the line under the two cases. One is single phase 2-wire system and another is 3-phase 3-wire system. Specific resistance of aluminum is this much ohm meter, that is the resistivity being given 2.85 into 10 to the power minus 8 ohm meter. So let us see. Now we know that from the power triangle, we know that if this is the base is the real power, hypotenuse is the apparent power, and this is your power factor. So P you can use directly to find out the real power as apparent power multiplied with cos phi. So 5 MVA is your apparent power multiplied with cos 5.8. You will get a real power of 4 megawatt or 4 into 10 to the power 6 watt. So this is the real power transmitted. The efficiency told to be 90%. It means there is a loss of 10%. So 10% of the power there is a loss, which is equal to 4 into 10 to the power 5. That is the power loss. Length of transmission, which is 50 kilometer, you can convert it into meter as 50 into 10 to the power 3. Then single phase 2-wire system, you know that complex power S is equal to voltage into current for single phase. So power is given S, apparent power is given, the voltage is given 33 kV. Now you can find out what is the current. So current you are getting as 151.5 ampere for a single phase 2-wire system. Then if the area of cross section is A1 considering and the line losses, because you have two conductors, so 2 I1 square R, where R you can substitute as rho L by A, then you can find out what is the area of the cross section. That comes to be 1.635 into 10 to the power minus 4 after proper substitution. Then the volume of the conductor material is basically volume is equal to area into length. As you have two conductors, so multiplied with 2 times area into length, you are getting 16.35 meter cube. Now for a 3-phase 3-wire system, similarly you know that the complex power now will become 3 √3 times the voltage and current. So here the voltage is basically 33 kV. Earlier you were having voltage into current, so that was a phase voltage. Now you have line voltage. So line current is basically 87.5 ampere, and then you can substitute to the loss with area cross section A2. Then you are getting the area cross section A2 as 0.818 10 to the power minus 4 meter square. Similarly, the volume is equal to area into length, but you have 3 conductors, so 3 into area into length. Substitute the value of area from here, and your length was 50 kilometer. Convert that into meter, and you will get 12.27 meter cube. So earlier your volume was 16.35, which was quite more as compared to the third case. So here we can see that if you have a 3-phase 3-wire system, you can have a saving of copper as compared to the single phase system. In problem number 6, you have a substation that is supplying a power at 11 kV with 0.8 power factor lagging to a consumer through a single phase transmission line, having a total resistance of 0.15. So you have a single phase transmission system. Now the resistance, total resistance is 0.15 ohms, and it is at 11 kV with 0.8 power factor lagging. The voltage drop in the line is 15%. So here you have a 15% voltage drop. Okay. Now, if whatever the power you are getting from here, if the same power is supplied to a 2-wire DC system by a new line and its resistance is equal to 0.05 with allowable voltage drop is 25%. So this is the voltage drop now. Calculate the DC supply voltage. So you have to determine the DC voltage. First, we will see for single phase system. Now, single phase system, the voltage drop is equal to I1 into R1. R1 is given to be 0.15 for single phase system. So your current you don't know. So consider this to be the first equation. Second, also it is told that there is a 15% voltage drop. So 15 by 100 into the total voltage will give you the second equation as 1650 volts as the voltage drop. So if you equate voltage drop for the two cases, 1 is equal to 2, you are basically getting a current of 11,000 ampere. Now you know that the power P is equal to S into cos phi. S is the apparent power and S is equal to voltage into current into cos phi. So you have the voltage and current. So voltage here is given to be 11 kV and current is also 11 kilo ampere. So you can obtain the power as 9.68 into 10 to the power 4 kilowatt. Now the same amount of power has to be transmitted using DC two-wire system. So the power 9.68 into 10 to the power 7 watt has to be transmitted to DC two-wire system. So what will be the new voltage and the load current? So load current I2 will be equal to power divided by voltage, which we have to find out, and voltage drop here has been given as I2 into R2, which is equal to also 25% allowable. So I2 current you can find out from here, and resistance is given to be 0.05. Also you know that allowable voltage drop is 25%, so you are getting 0.25 if you give it at 11 kV. So if you find out for the voltage, so it is 0.25 into V, that is we find out. Okay, then you can have the product V square if you equate the voltage drop whatever you are finding that. So if you equate it, so you'll find a relationship with the square of the voltage as 1936 into 10 to the power 4. This voltage you can find out with taking the under root, which you are getting 4400 volt. Okay, 4400 volt you are finding out for a DC two wire system when the power, same power is transmitted with respect to the previous case. So here you have to find the voltage. Next problem that we are going to discuss is problem number 7. So problem number 7, you have 3-phase 4-wire system which is used for lighting. Compare the amount of copper that is required for a 2-wire DC system with the same line voltage. So line voltage has to be the same. Assume the same losses. So losses has to be same and load is balanced. So these are all givens, and neutral wire is 1/2 of the cross section of the respective outers. So let us see. So if you have a 2-wire DC system, now voltage is V, power is P, and R1 is the resistance. So you have the relationship as current is equal to power by voltage and power loss is 2I1 square R1. So substitute the value of the current in the formula. Now if it is a 3-phase 4-wire system, then the voltage that you will have is line to neutral voltage and R2 is the resistance of the wire. Then power is equal to 3 times the voltage into current into phase. Since you have taken here the voltage has to be the phase voltage, you are using a formula 3 times the voltage into current. So you are getting 3 VI2 considering that cos phi is equal to 1. So power loss that you have is 3 times I2 square into R2, where you substitute the value of the current I2 as power divided by 3 V because you have 3 voltage. Okay, 3 times. So this you are getting the power loss. Now we have been told that power loss is equal for all the two cases. So equate it. On equating, you are getting a resistance R1 by R2 is equal to 1 by 6. Now if the resistance is R1 by R2 is 1 by 6, and you know that R is equal to rho L by A, where area and resistance are inversely proportional. So here you can have the area to be your A1 by A2 to be reciprocal, that is equal to 6. Okay, so the copper required for the two-wire system will be equal to the volume of the copper required will be area into length, and since it is a two-wire, the 2 times area into length, and for the three-phase four-wire system you can have 3 times area into length plus L by 2 is the length for the neutral wire. So just you take a ratio of both the things, copper for three-phase system and copper for DC system. So for a three-phase system you are getting 3.5 times the area into length, and for a DC system you are getting 2 times area into length, and you have already found out the relationship between the areas, so that you put it 1 by 6 and 3.5 by 2, so you are getting 0.292. So for the three-phase system, you are getting 0.292 into copper for DC system. So thus we are able to find out the volume of the copper. Now in the last problem, problem number 8, we are going to estimate the weight of copper that is required to supply a load of 100 megawatt at unity power factor condition by a three-phase 380 kV system over a distance of 100 kilometer. The neutral point is earthed. Okay, the resistance of the system can be assumed to be 90%. So let us see. So power loss is basically, because if you have 90%, so power loss is 1 minus 0.9 into 100, that you are giving it 10 megawatt. Line current, whatever you are getting, is basically the formula for power. You have 100 megawatt power, so power is equal to root 3 times VLIL cos phi. That formula you can use to find out the power equation. Now it is a unity power factor condition, so you can assume it to be 1, and power is 100 megawatt, root 3, voltage and current are given, so you are getting 152 ampere as the line current. Now you have 3 conductors, so 3 conductors together make a line loss of 10 megawatt, 10 into 10 to the power 6. So one conductor will give a power loss of 10 megawatt by 3, so 3.33 into 10 to the power 6. Now the resistance per conductor, if you want to find out, so you have to use the formula that if you have 10 megawatt, so that you divided with 3 and then you multiply it with 152 square, so you're getting 144.3 ohms. Now this is the resistance per conductor you have obtained, but what about per kilometer length? So totally the length is 100 kilometers, so you are getting 1.443 ohms. Then the conductor cross sectional area that you have to find out is, after obtaining the resistance, conductor cross sectional area if you want to find, then it is equal to 0.045 divided by the resistance, so you are getting 0.03 meter cube. Volume you per meter 0.03 into 100, so it is 3 centimeter cube. Weight, now you have to find out for 100 kilometer length, what is the weight? So weight, you have volume into length, that you have to multiply. So you have for 100 kilometer, if you multiply it for the volume that you have found out, so you are getting a 9000 kg. So in this particular problem where you have 380 kV system, 380 kV system which is 100 kilometer long, and you have to supply a power of 100 megawatt by a three-phase system. So whenever you have a three-phase system, you have to convert into corresponding single-phase system by dividing with 3. So there you can find out how much weight of copper you have to use. So it is coming to be 9000 kg. So this completes the tutorial number 8. Thank you.